Hi everyone, this is Mrs. Sharrow, and in this lesson we are going to look at two polynomial theorems in 2.5. We're going to start by taking a look at the fundamental theorem of algebra. So the fundamental theorem says that the degree of the polynomial is equal to the number of zeros, both real and imaginary, including their multiplicities. Now, another name for zeros, sometimes we call them roots. They are also solutions to setting our polynomial equal to 0 and solving for x. So for each polynomial, some things that we're going to think about is first, how many zeros does the polynomial have? And according to this fundamental theorem, we're just looking at what is the degree. And second, the fastest way to find all the zeros of a polynomial is to factor, set each factor equal to 0, and solve for x. So we're going to ask ourselves the question if the polynomial can be factored. If yes, that's how we will move forward. If not, we'll see here in a moment some other things that we can do. So let's look at this first polynomial. We're wanting to find all of the zeros for this, and thinking about a factoring strategy, we always want to start by looking for a greatest common factor, and in this case it doesn't look like we have one. And so next we can notice that this has 4 terms, and sometimes if a polynomial has 4 terms, the way that it works to be factored would be to factor by grouping. So we can try that by grouping together the first 2 terms, grouping together the last 2 terms, and what we're wanting to do is take out the greatest common factor from each group. Now in the second grouping, there really doesn't seem to be anything in common between the 11 and 12. We could take out a -1, something like this, turning it into 11x plus 12. But what we need to notice here is that the quantities in parentheses are not the same, and because of that we will not be able to use the factor by grouping method. So since it cannot be factored, we're going to need to do something else. Zeros. If they are real zeros, they show up as x-intercepts on the graph of the polynomial. And so let's go to our calculator and see what the graph shows in terms of the x-intercepts. So we're just going to type our function in exactly as it's stated. So we've got x cubed plus 2x squared minus 11x minus 12. I'm going to double check my window and change it back to -10 to 10 in both directions. We can always go back and adjust our window if we want to zoom in on something or even zoom out, but this is a pretty good place to start. And it looks like we have 3 perfect x-intercepts. So we see one at -4, we've got an x-intercept at -1, and an x-intercept at +3. So let's make a note of that here, that the graph shows the x-intercepts at -4, -1, and +3. And because the degree of the polynomial was 3, it makes sense that we are seeing 3 zeros. And the value of the zeros are where the x-intercepts were, -4, -1, and +3. All right, so let's look at the next one. Again, if we were to try the factor by grouping method here, we would see it didn't work. The quantities in the parentheses would not be the same. So we're going to go to our calculator graph again and look for an x-intercept. So go ahead and go back to our y equals. We have an x cubed at the start of this one. I'm just going to type a 7 over the 2. I'm just going to change this to a plus 11x, and then we've got a -3 at the end. All right, so we'll take a look at what the graph shows this time. So it looks like we see 3 x-intercepts again, which is exactly what we would expect. Again, this one has a degree of 3, so there should be 3 zeros. However, when we're finding our zeros, we want to give the exact value for each zero. So notice how the one on the far left and the far right, it looks like those are in between whole number values. So if we were to estimate its location, it would be a decimal approximation. It wouldn't be exact. The one here, we see that that looks like, yep, that's right, going right through -3. So what we're going to do is just focus on the nice whole number x-intercept, or in this case integer value. It's at a -3, and we're going to do a little bit of something with that. So let's make a note here that the graph shows an x-intercept at -3. So that means that -3 is a 0. And if we think about some things that we've been talking about earlier on in Chapter 2, if -3 is a 0, that means that x plus 3 is a factor. And so we can actually divide our original polynomial by this factor x plus 3, and that would tell us what the other factor is, that when multiplied by x plus 3 equals the original polynomial. So remember that polynomial division can be a way to help us get a polynomial factored if another factoring strategy didn't work. So we have the x plus 3 here, so we can do synthetic division on this. We'll go ahead and start by turning it into a -3. We'll always look out for missing terms. In this case, it doesn't look like we have any, so we'll go ahead and list our coefficients and the constant term across the top, and we'll go through our synthetic division here. It makes sense that we get a remainder of 0 because we already saw that -3 was an x-intercept on the graph. So let's go ahead and take this result and write it as a polynomial that it represents is really x squared plus 4x minus 1. And what we can do with that is we can now write the original polynomial f of x as a product of two factors being multiplied together. The factor x plus 3 that we divided by, along with this x squared plus 4x minus 1 was the result of doing our division. So the idea is that if we were to multiply these out, we're going to get the same polynomial that we started with. Now, looking at this part here, if we tried to factor this further, it doesn't look like the numbers are going to work out. We'd have to have two numbers that multiply to -1 and add to +4, but it's just not going to work out that way. And so in a sense, it is factored. We do have a factored form here. So moving on to the next step, once it's factored, we'll go ahead and set each factor equal to 0 and solve for x, and those solutions will be our zeros. Now we already know that -3 is one of our zeros. We'll circle that. And this one over here, so it's a quadratic equation because we've got the x squared there. We're not able to solve it by factoring, so the next easy way to solve it is to use the quadratic formula. We can say here that a is 1, b would be 4, and c is -1. So plugging that into the formula, we have x equals -b, so that's going to be -4, plus or minus the square root of b squared, so that becomes 4 squared, minus 4 times a times c, all divided by 2 times a. All right, so let's simplify this down. So inside of our square root, we've got 16, and then this is -4, but then it's being multiplied over here by a -1. So that it's kind of like -4 times -1 will turn into +4. So it's like we have 16 plus 4, which is 20. Now we can split that 20, square root 20, into square root 4 times square root 5. Just kind of simplify this down, and we know that square root 4 is 2. So a simplified form of that would be -4 plus or minus 2 times the square root of 5, all divided by 2. Now what we can do for a final step is we can divide each term on the numerator by 2. So -4 divided by 2 is -2, plus or minus 2 square root 5 divided by 2 is just going to be 1 square root 5. So what we have represented here is the exact form for the other two zeros. Now, we've written them together using that plus or minus sign, but I want you to see that it really represents two different values. So we've got negative 2 plus square root 5, and we've got negative 2 minus square root 5. So there's our three zeros, which makes sense for having a degree of 3. One final thing I want to show you in this problem, if we were to take the negative 2 plus square root 5 and negative 2 minus square root 5. The decimal approximation we get here is about 0.24 and negative 4.24. Well, that's the location of the other x-intercepts we saw. So look at this one right here. That's the 0.24. And this one over here is the negative 4.24. So they did show up on the graph, meaning they're real zeros. They're not imaginary. Imaginary zeros don't show on the graph, but we wanted to get their exact form rather than a decimal. And the only way to do that is by doing the algebra, doing our synthetic division, and then going through the steps for our quadratic formula. All right, let's go ahead and turn over to the next side. All right, so this next one, the highest exponent we see here is 4. So let's make a note that our degree is 4. And so at the end of this, we should have 4 zeros. So there's really no way to factor something like this. So again, we're going to need to start by going to our calculator and typing this in. So we've got x to the 4th minus 6x to the 3rd plus 10 x squared plus 2x minus 15. All right, so we're going to see what our graph shows. Looks like we've got a 0 at negative 1, and we have another 0 over here at positive 3. It's only showing 2, but since the degree was 4, that means that we should have 2 more. This is telling us that the other two zeros are imaginary zeros because those aren't going to show up on the graph. So let's do something with the zeros that we see, the negative 1 and positive 3. Let's make a note of this here, that the x-intercepts we saw on the graph are at negative 1 and 3. So this means x plus 1 and x minus 3 are factors of f of x. So just as we did before, in the last problem, we're going to do synthetic division to divide our polynomial by not one, but both of these factors. The result that we get there should be something that's quadratic that again we'll be able to put into the quadratic formula. Now it does not matter the order that you do your division. Let's divide by x plus 1 first. So we'll go ahead and turn that into a negative 1. Always double check here for missing terms. Doesn't look like we have any missing terms here, so we'll go ahead and list out our coefficients and the constant term at the end and go through the steps of our synthetic division. And again, it makes sense here that we get a remainder of 0 because we know that x plus 1 is a factor. Now, rather than writing this out as the cubic polynomial, 1x cubed minus 7x squared and so on, let's actually just keep the numbers there in the row and immediately start the division by x minus 3. So we can just turn that into a positive 3. Put that in a box there, so just sort of stacking our division one on top of the other. Bring down the 1. We'll go through our synthetic division steps on this one. And again, we get another remainder of 0, which is what we would expect. Okay, so now we can take this result. This now represents something that's quadratic. So we've got 1x squared minus 4x plus 5. And what we can say here is that our original polynomial can be written as a product of factors x plus 1 and x minus 3, based on the x-intercepts that we saw, multiplied by the result of the division. If we were to multiply it all out, we should end up with the same thing that we started with. So our synthetic division here helped us to get this polynomial factored. Now, if we take a look at this one here, and if we try to think about two numbers that multiply to 5 and add to negative 4, it almost seems like it could work. But if we think about factors of 5, we have 1 and 5, which doesn't work, negative 1 and negative 5, which doesn't work. So we're not going to be able to factor this one any further. We'll go ahead and put it into the quadratic formula, just as we did the last one. And in this case, we see a is 1, b is negative 4, and c is 5. So we've got x equals minus b plus or minus b squared minus 4 times a times c, all divided by 2a. Now it makes sense that we are using the quadratic formula to solve it because we know that the other zeros are imaginary, and we would only get the imaginary zeros through an algebraic process like the quadratic formula. We wouldn't be able to get those by factoring. All right, so inside our square root here, so we've got a positive 16 minus 20. 16 minus 20 is negative 4. So that's the key there, that any time we're doing the square root of a negative, it's representing an imaginary number. So we could split this into the square root of 4 times the square root of negative 1, because the square root of 4 is 2, and the square root of negative 1 is I. Then again, we can divide each part of the numerator by 2, and we get 2 plus or minus I. So listing out our final answer for the 4 zeros, we had negative 1 and positive 3 from the graph. They showed up as x-intercepts. Then we have the imaginary zeros, 2 plus I and 2 minus I. You can write them with the plus or minus symbol, but I just want you to see here that it really represents two different solutions, and that's giving us our full list of 4. I'm going to save this last one for you to try on your own. One thing to pay attention to is that we are missing the x cubed term. So we want to think about filling in a 0 in its place when you get to the point of doing your synthetic division. This isn't one that can be factored, so again, we're just going to go straight to our calculator, look for an x-intercept, and go from there. When you have your solutions all the way worked out, you can check them here. The final answer for your zeros should be negative 1, positive 3, negative 1 plus 2i, and negative 1 minus 2i. So take a moment, try it on your own, and check to see that you got this for your final answer.